Hi, everyone. I'm Kristen. I head up corporate communications at FDNA. Just wanted to say welcome, happy Halloween, and thank you all for joining us today to hear Dr. Karen Gripp of FDNA and Dr. Alka Chaubey of PerkinElmer Genomics discuss a new platform for genetic testing created by the integration of next-generation phenotyping into next-generation sequencing and success cases that have resulted. So with that, we'll have Dr. Gripp kick us off.
Welcome, everybody. I'm Karen Gripp. I'm a clinical geneticist and chief of the Division of Medical Genetics at the Dupont Hospital for Children in Wilmington, Delaware. And I'm also the CMO for FDNA. Today, I will start the presentation by introducing you to Fiesta, a machine learning tool that supports clinical geneticists. And I will talk to you about next generation phenotyping with some specific examples. We will then talk about the seamless integration of next generation phenotyping into variant analysis through Fiesta labs. And at that point, I will hand off the presentation to Dr. Alka Chaubey from PerkinElmer Genomics, who will talk about what this integration of next generation phenotyping looks like from the lab perspective, and how improved variant ranking and shortened turnaround time can shorten the diagnostic odyssey for patients and really move towards fulfilling the promises of precision medicine. So let me introduce you to Deep Gestalt. Deep Gestalt is the algorithm that drives the Fiesta application. Fiesta is an application that is available free of charge to clinician users, and it's currently being used in about 2,000 clinical sites in 130 countries. The Fiesta app is HIPAA as well as GDPR compliant, so it is absolutely allowed to be used in a clinical context. The Fiesta application is driven by the Deep Gestalt algorithm. And this is a deep convolutional learning-based algorithm that supports the facial analysis. We have recently been able to publish a landmark paper, as shown here in Nature Medicine, that describes in detail how Deep Gestalt was trained, how it performs, and it puts out landmark standards for performance in this context. Currently, Fiesta supports more than 300 specific genetic syndromes and syndrome groups that Deep Gestalt has been trained on. And because these are the more common conditions, they represent about 45% of all cases that can currently be diagnosed by whole exome analysis. So let me show you what this looks like in the hands of a clinician. As a clinician, using my mobile device, I can take a picture of the patient in the clinic visit. And this is a picture of one of my patients taken in a clinic visit. The app analyzes the facial features, and that is what we call Gestalt analysis. This is based only on the facial photograph of the patient, and the facial photograph is analyzed. The analysis is then compared to the many syndromes that the system has been trained on, and the system then ranks these syndromes by how similar they are to this patient's facial features. So what you see here is that for this particular image, for this patient, Smith-Lemli-Opitz syndrome is the highest ranking or the top one match based on the Gestalt analysis. This is this bar on the left. And then you have other conditions in position 2, 3, 4, and so on. So it gives you the rank for how closely the facial features of the patient match to these conditions. This is a very useful tool in clinic, and it has been proven to be useful in different ethnic contexts also. That is a concern that is often raised. So for example, here is a publication by Dr. Mishima from Japan, who used this tool in a Japanese clinic, and what he found is that in 42 out of 49 patients who were ultimately diagnosed with a condition that the Deep Gestalt tool is trained on, 42 of these were included in the top 10 matched syndrome, so showing excellent performance in this Japanese cohort. And similarly, for a US clinical cohort, Dr. Zaradi was able to show that for those conditions on which the system has been trained, 91% of patients had that condition included in the top 10 matched features and 100% in the top 20. So this is based on Gestalt match based only on a facial photograph. You all know that a phenotype consists not only of the facial findings, but also of everything else that encompasses and entails the patient. So we also have feature match to supplement the facial analysis. So features can be submitted in HBO terms as shown here. And when we look at my clinic patient, these were findings that he had. When we allow the Fiesta gene tool to also use these HBO terms to perform a feature match, then we have ranking of the syndromes not only based on Gestalt, but also on the feature match, as you see here in the bar to the right. And when we look at this particular patient, you see that again, Smith-Lemli-Opitz syndrome is the #1 ranked condition. You see many other conditions ranked as well. If you go to your desktop version of Fiesta gene and you don't want to type in each HBO term for a patient, what you can do is you can open up your case. And when you click on this blue bar here that says extract features from clinical notes, you will have the option to use a beta version of a text to phenotype analysis program, a program that is able to do natural language processing and that can suggest HBO terms based on that patient's clinic note. So when you click on this blue bar, this page comes up and you have this box here where you can cut and paste the clinic note for your patient. So I've added here a very much abbreviated clinic note for my case. You're well aware that typically clinic notes are much, much longer. So we pasted it in here and then we click on this blue bar that says extract features. And when we do that, the system lists all the HBO terms that were identified in the note to the right. And the clinician only has to go down this list and click to select those HBO terms that are applicable to this case. So as an example here, this patient has a family history of breast cancer that was not applicable to the patient, but it was listed because it's in the note. So this is something that as the clinician, you would not click to include in this analysis. When you are satisfied with the HBO terms you've chosen, you click apply here, and then it brings you to the same place where for your patient, you have the complete analysis, including Gestalt and features. So for this case here, this was a clinic patient of mine, and based on the very strong suggestion by Fiesta gene that Smith-Lemli-Opitz syndrome might be the right diagnosis in combination with my own clinical judgment, I thought that this was a very likely potential diagnosis, and we were able to order targeted testing. So in this case, this patient was diagnosed with Smith-Lemli-Opitz syndrome without ever requiring anything other than targeted testing. And I think this is a really important point to make, that this is Fiesta gene is a powerful tool in the hands of a clinician, but it does not replace the clinician. It does not take away from clinical decision making. Rather, it is an additional tool that a clinician can use to get another objective assessment of facial features as well as HBO terms and potential differential diagnosis for the patient. So for this particular patient, we were able to make a specific diagnosis based on targeted testing. The Fiesta gene tool is very powerful, and it's even better when it's combined with next generation sequencing technologies, such as, for example, exome analysis. This is an early paper we published suggesting to apply next generation phenotyping in combination with next generation sequencing. And more recently, Dr. Peter Kravitz and his group have been able to perform a large study looking at prioritization of exome data by image analysis. This report was recently published in Genetics in Medicine for anybody who's interested in more detail. We're going to briefly review his study. In the PEDIA study, 679 cases were analyzed, and for each of these cases, a specific diagnosis was made using exome analysis. So we have a pathogenic disease-causing mutation for each case. HBO terms are available, and these are because these are handpicked cases. There's a lot of clinical information available on each patient, and for each patient, a facial photograph was available. The PEDIA algorithm then performed analysis of the variant data for a CAT score. The facial photograph was analyzed and the Gestalt score was created. And similarly, the HBO terms were analyzed using a number of different tools. And then the PEDIA algorithm provided a score for each gene, ranking on how likely this gene was to be disease-causing for that particular case. When we look at the results for the top one accuracy, using only the CAT score, 16% of genes would have been scored accurately. When we look at the top 10, so the 10 highest ranked scores based only on the CAT score, 41% of cases would have been appropriately included. When we then add the feature analysis, the top one accuracy increases to 50%, the top 10 accuracy increases to 83%. If, in addition to that, we also use the Gestalt analysis looking at the facial features, the top one accuracy is now 90%, and the top 10 accuracy is 98%. So very impressive data suggesting how powerful next generation phenotyping is when you combine it with next generation sequencing tools. So despite these impressive data from the PEDIA study, there are some limitations to the study. For example, each of the cases was manually curated and was very richly annotated with HBO terms. And that is not necessarily the case in clinical diagnostic labs, where you know that the case sometimes come in with very little additional information. Further, the cases were analyzed in many different laboratories, and every case did not necessarily have the full VCF file available for analysis. So for some cases, the exome data was simulated and the pathogenic variant was spiked in. So there are some limitations to the PEDIA study. And we then partnered with the Greenwood Genetics Center in order to further perform validation testing on this approach. So in the Greenwood Genetics Center, a single lab, 126 exome cases have been performed that we were able to analyze. And of these, 45% are considered solved, 53% are considered unsolved. This breakdown is very similar to what you have seen from other large labs publishing exome data results. The solved cases can be further divided into those that are easily solved and those that are somewhat challenging. So for example, that require trio analysis in order to make a definitive diagnosis. So what we see here is more real-world data for exome analysis in a single lab. When we look at the data from this study, we see that looking at, for example, the top 5 ranks or the 5 highest ranks, when we look only at the CAT score, about 11% of cases would have been included in the top 5. And this is similar to the GGC rank. This is an internal pipeline that also uses an outside vendor for a software that ranks potential disease-causing genes. We would have come up with similarly about an 11% rate in the top 5. And this is very similar to what's being used in many other labs as a proprietary analysis software. Now, if we perform PEDIA study analysis, we would have included almost 70% of cases in the top 5 ranking. And if you push this out to top 10, 15, and so on, you see that the PEDIA rank would continue to be vastly superior to only CAT or internal pipeline analysis ranking. So here you can see how powerful it is to incorporate next generation phenotyping into the variant analysis pipeline. Showing here is the roadmap for next generation phenotyping when applied to next generation sequencing. Such AI-driven phenotyping will really become an intricate part of precision medicine, and it will hopefully help to shorten the diagnostic odyssey for patients. So we've so far talked in more detail about the facial analysis, the feature analysis, and the clinical notes. In the future, we will look at many additional ways to assess a phenotype, and this will also become available to clinicians. What is really exciting today is Fiesta Gene Labs, a new functionality in the Fiesta Gene tool. Fiesta Gene Labs allows clinicians like me to directly share our next generation phenotyping data with a laboratory that will perform the next generation sequencing testing on our patients. So what you can do here is, as the clinician, when you look at your case, you perform your next generation phenotyping analysis, as we've reviewed in some detail, and then you can choose the lab that you want to share your data with. So for example, PerkinElmer Genomics has fully integrated this in their workflow. If we were to click on that lab, it would take us to a page where I, as the clinician, can put in the identifiers for the patient. I can make a choice if I want to share this patient's photograph, but I don't have to share the photograph itself. If I do not include the photograph itself, the abstracted data that was used in the Gestalt analysis is still available to the laboratory. The image itself will not be shared. So when I have prepared the case, I can then click to share the case with the laboratory. And at that point, the lab, like PerkinElmer Genomics, would have access to the next generation phenotyping data and can directly apply this into their variant analysis pipeline. And this is where I'm handing off the presentation to Dr. Alka Chaubey, the head of Cytogenomics at PerkinElmer Genomics, who will tell you more about the integration of this new tool into their analysis pipeline. Alka, take it from here.
Good morning, good afternoon, everyone. Thank you, Karen, for this introduction. So as Karen mentioned, I am the head of Cytogenomics for PerkinElmer Genomics. And what I'm trying to show on this slide here is that PerkinElmer Genomics is part of a big global laboratory network where we have laboratories in India, Malaysia, China, and of course we have our sequencing capabilities in the US. So with this kind of laboratory network, it becomes extremely important that do we have the right tools to build an enriched data set from diverse populations across the globe in order to provide improved and tailored variant interpretation for any genomic testing for disease diagnosis. So how does PerkinElmer go ahead and integrate a tool like Phase2 Gene Labs into our global network for disease diagnosis? So what we have here on this slide is that PerkinElmer Genomics has a LIMS system, which is extremely important for accessioning all the global samples that come our way. And of course, then we have a very exhaustive bioinformatics pipeline where you can see that we have our own PerkinElmer applications. Along with that, we also have external applications and commercially licensed resources that we use. And with that, we also have our proprietary database or software which is utilized for reporting genetic tests. It's called ODIN, Ordered Data Interface Network. And you can see over here that one thing is that we do rely on phenotype-assisted analysis, and this is where I'm going to walk you through certain cases. And then, of course, the variant classification and everything post getting the variants in hand are as per the ACMG guidelines. And we have a pipeline for variant analysis review, and then, of course, an ABMGG certified director who signs out those cases. And of course, with integration with multiple databases is also something that becomes very important. And all of this, we have exceptional quality assurance program and audits and everything to make this exhaustive network functional for our offerings. So I want to introduce Odin for those that don't know this. And this is exactly how this web-based Odin looks like. So you can see over here that all the genomes or exomes or our next generation sequencing tests are interpreted by a board certified geneticist. And you can see that when the data is uploaded into Odin, then this is essentially how all the variants will show up. So we do have a master variant list, a master gene table, and in here, you know, everybody who is on this call that are used to running these tests probably are aware that hundreds and thousands of variants will show up in any case. So how do we weed through? How do we use the phenotype information and a tool like Phase2Genes in our pipeline is something that I'd like to share in the next coming slides. So in Odin, we have a phenotype filter. And this phenotype filter, they have been created in Odin and they are linked. And the Phase2Gene labs, as Karen just mentioned, they can be accessed from our filter page. So we have a filter section, as I showed you on the previous slide. And from here, we have this Phase2Gene labs, which if we check this little button over here, we can click on this and we can go to the Phase2Gene labs portal. So once you click on that, then this, as Karen again mentioned, this is HIPAA and GDPR compliant. So no issues in getting the information over here. So this allows the user to upload the file containing the phenotypic terms or enter on the interface itself. So we can collect, and you can see that either files can be uploaded or text can be entered. And Karen gave a wonderful example of even, you know, from a lot of text where the phenotypic information can be extracted. And then this can be, once you click on the submit over here, depending upon which part you're using, then you will be taken to this analyze, collecting the data. And you can see here, or maybe you cannot see, but you know, terms like epilepsy, global developmental delay, ptosis, and these phenotypic terms will show up. Once you click on analyze, so you can see here, you collect the phenotypic information and then you want to analyze. So then suggested features that you have entered will show up. So this is kind of like a place where you can double check that everything that you entered, tremor, long phase, seizures, protruding tongue, and so on and so forth, are you in line with that? Along with that, it will also suggest a list of genes that may be associated with those phenotypic terms. So one, the Phase2Gene labs uses natural language processing to extract keywords, and then these are entered to match the phenotypes to the ones in our database. Once we click submit from here, it takes us back to our Odin page where the list of genes will be displayed over here as a list, or you can also click on display genes and the entire gene list will show up over here. So I'm going to walk you through 3 cases. One, a focused exome with copy number variation analysis, the other a whole exome with deletion duplication analysis, and the third case will be a whole genome. So essentially, once you click next, any variant from the gene list over here in your patient sample is the only thing you will see in Odin. So the first case that I want to talk to you about is this case that came in with the following clinical features: laryngomalacia, bilateral proptosis, craniosynostosis, mild facial hypoplasia, and had tracheostomy done, and also had dysmorphism of low set ears. There was no previous testing performed on this individual's sample, and the test that was requested was a focused exome analysis with deletion duplication analysis. I don't want to bring your attention to, when you look at craniosynostosis genes. So when we put these features in, so using these clinical features, obviously the top two syndromes you can see over here, Cruzon syndrome and Marshall-Smith syndrome showed up. Along with that, there were a lot of genes because you can see there is a variability in these phenotypic terms. But the top gene over here, which most everybody might be aware of associated with craniosynostosis, is FGFR2. Now remember, we do have FGFR3, FGFR1, TWIST1, EFNB1. These are the genes associated with something like craniosynostosis. So once this was submitted in this patient's focused exome data, what we saw was that only one variant showed up. And this was in the FGFR2 gene. This was a threonine 341 to proline change. You can see the alt fraction over here. It was a heterozygous change. We know this is an autosomal dominant disorder. This has been previously reported in HGMD, which you can see over here. And you can see the variant statistics over here. So how did we report this is that this FGFR2 variant of autosomal dominant inheritance is associated with FGFR2 related disorders. So if you go to OMIM, for example, you will see that there are 12 to 14 disorders associated with FGFR2 gene. Now, what I've highlighted over here with Cruzon syndrome is laryngomalacia, proptosis, craniosynostosis, mild facial hypoplasia, and tracheostomy. So this is how this was reported. So the second case is an example of, well, when you have some phenotypic information that is really broad and you don't know what to do in that situation. So this is a case from a 12-year-old male and the clinical features that were submitted were abnormal renal morphology, renal tubular dysfunction, renal stones, familial hypomagnesemia with hypercalciuria and nephrocalcinosis. Again, this patient also did not have any previous testing, and the test performed was the whole exome sequencing along with deletion duplication analysis. So going again to the phase 2 gene labs filter and the ability to analyze the phenotype. So, we have tons and thousands of variants that show up whenever an exome is performed. And when we put these phenotypic terms over here, a lot of genes, showed up. But the one that I want to bring everybody's attention to is this AGXT gene. This is the alanine glyoxylate aminotransferase gene. And this is associated with hyperoxaluria, which is an autosomal recessive disorder. So let's see what happened over there. So when we use this filter and when we saw the variant show up, you can see that from the list of genes, we had two variants that showed up. One was this homozygous frame shift variant in this AGXT gene that showed up, and a Notch2 variant that showed up. So moving further, when we look at the OMIM disorder associated, then the one that really is consistent with the diagnosis or the clinical features in this individual is AGXT associated with hyperoxaluria primary type 1. And again, I've highlighted the consistent features, the renal tubular malfunction, the stones, and this disorder is actually characterized by an accumulation of calcium oxalate in various tissue types, especially the kidney, and that is what causes the renal failure. And so affected individuals can have either decreased or absent enzyme activity, and that is what leads to the overproduction of oxalate and the accumulation of calcium oxalate in various body tissues. So this one again, clearly shows that when you have this kind of renal morphology, the phase 2 gene lab portal and this feature can be extremely useful in this situation. Also, what we saw was that, this variant appeared to be a homozygous variant. And when we saw that this was actually within a 6.4 megabase AOH block on chromosome 2q. So it was truly a homozygous change and not a variant and a deletion on the other allele. So this was, again, another clear example of the utility of using the phenotypic features to be able to do the variant analysis. The third case, and I mean, this gene is pretty special. And if anybody from Greenwood Genetic Center is hearing this, they'll probably appreciate is that this was a sample from a 4-year-old female with global developmental delay, infantile epilepsy, muscular hypotonia, hyperreflexia, generalized seizures, and of course, a neurodevelopmental disorder. Again, there was no previous testing performed on this patient, and the test ordered was a whole genome sequencing. And of course, with this kind of diverse phenotype, once you start trying to find the genes associated with this conglomeration of phenotype, you're going to get a huge list. So of course, the gene that I've highlighted here is MECP2, and this is the methyl CpG binding protein 2, which is associated with X-linked dominant and X-linked recessive disorders. And so when we utilize the filter, and of course we have a different pipeline for CNV analysis, what we saw was that there was a deletion of 2 exons involving the MECP2 gene, which you can see very clearly over here. And when we reported this, obviously we reported this as pathogenic, and of course MECP2 and its association with Rett syndrome in females, where global developmental delay, epilepsy, hypotonia, and neurodevelopmental phenotype with the classic, dysmorphisms are actually consistent again with the phenotype, and we call this a pathogenic change. So I hope that I have been able to demonstrate to different laboratories, and Karen has been able to show that utilizing the features, the deep gestalt, along with the phenotypic features, using the HPO terms is an extremely advantageous tool, which we have found in our experience. And we are yet to actually have the clinicians start using the app to be able to submit the photographs of the patients for an enhanced analysis. So we have some clinicians in India and Malaysia that are doing a beta test right now, and hopefully they will be able to see the benefit of having those features being utilized for genetic testing. So with that, I will be happy to answer any questions that anybody might have.
Okay, great. Thank you both for a wonderful presentation. The first question we have here is for Dr. Gripp. Does the clinician have to type in clinical notes?
You don't have to. You can use only the Gestalt analysis, which uses only the facial features. If you do not want to put in the entire note, you can only hand type in a few HPO terms or a few findings in the patient that stood out to you. So you can use that way to pick HPO terms that are analyzed in the feature analysis. You do not have to use the entire note. It's just another tool that is available, and I find it really helpful because for me, when I can put in the entire note and I have the list of HPO terms available for easy clicking, I will be reminded of findings that seem minor, like clinodactyly, that I might not have remembered to type in for my case. So I find when I use this, that my annotation is more complete than if I just by memory put in the few things that stood out the most to me. So it's a different tool that is available, but it doesn't have to be used.
Okay, great. Thank you. Dr. Chaubey, when prioritizing the exome data, are only photographs taken into account or also the clinical information with the HPO terms?
So if we got the photographs, then great. Otherwise, the entire clinical information that was provided with the HPO terms were taken into account.
Great. And back to Dr. Gripp. What are the most important features when the system recognizes a syndromic face?
That's a tough question to answer because it really depends on each case. If you have the app open, you can click on the heat map and that will indicate to you which areas of the face were most used in this particular case to make a correlation. So the answer depends on, for each patient, it varies what stood out the most, what matched most closely to any of the conditions that the system has been trained on. It is not a one answer for all cases.
Great. Back to Dr. Chaubey. What are the top 3 areas this tool can be used for?
So I think that what we need to keep in mind is that with all the information that we are getting now with the exome testing and the genome testing, what we are finding is that there is considerable overlap in the phenotypes of different syndromes and associations. And this is where this can serve as a very good tool. So in my opinion, and what we have seen is that especially for number 1, differential diagnoses and expansion of phenotypes. So we had a whole genome case where we had Cockayne syndrome, UPD5, and a trisomy 21 phenotype. So this is where, you know, not only can you have multiple diagnosis syndrome, but also expansion of phenotypes. So those are the 3 big areas that I think that this would be extremely beneficial for.
Great, thanks. Dr. Gripp, if someone uses an iPad that uploads directly into their Epic system, can they insert the picture into Face2Gene?
You would currently have to screenshot the picture and then put it into a Face2Gene. So yes, if you have the images available using any of the ways how you can input images into Epic, you can subsequently use that image in Face2Gene, but you have to screenshot it and import it into a Face2Gene.
Here's another one as well. I guess both parties could feel free to answer, but does lab software integrate with other systems beyond Odin?
I believe so. I am aware of Odin because I'm part of PerkinElmer Genomics, but Karen, what about other laboratories?
So yes, there are different ways to integrate this tool. It does not require one specific way to integrate it. For anybody who has this question, I would encourage you to please contact info@fdna.com because the people who are responsible for the integration, the technologists, can answer your questions more specifically, more appropriately to your lab setup. So there are different ways to integrate this tool. It's not a one size fits all, and the team can work with you on the specifics.
Great, thank you. Also, Dr. Gripp, you mentioned that Face2Gene is free of charge to clinicians. What about the desktop tool used for text to phenotype analysis and for Face2Gene labs? Also, does a clinician have to purchase access to this?
Good question. So the Face2Gene app, as I said, is available free of charge to clinicians. And this is one tool that encompasses the use on a desktop. This encompasses the use of the text to phenotype as well as Face2Gene labs, the ability to push the data directly to the lab. All of this is part of the Face2Gene app that is available free of charge to clinicians, and that is HIPAA and GDPR compliant, which is the most important piece of information, I believe, for clinicians to always be aware of.
Great, thank you. Another one, is this available on mobile?
Yes, the Face2Gene app is available on mobile, so on app as well as on other iPhone and other mobile handheld devices. It is absolutely available. Some of the functionalities have to be used on the desktop version currently, so that we are improving the mobile version to include more. Right now, you can take the pictures and you can use this app on a mobile device. The text to phenotype application is currently available on the desktop version.
Okay, great, thank you. So I believe that's about all we have time for, but I think we answered the majority of the questions. So unless there were any that were not addressed, please again, feel free to send them to info@fdna.com. And thanks everyone again for joining us today. And thank you both, Dr. Gripp and Dr. Chaubey.
Thank you. Bye.
Thank you. Bye.